Okay, so that's the second lecture. I will continue with the stuff I talked about last time. Just to remind you, so I was talking about interferometric experiments, so that would be matter wave interferometry experiments, and there was this specific scheme which I told about last time, and there's this first part which has to do with levitated optomechanics, basically trapping a nanoparticle. And I will talk about the experiments we do in Southampton to trap nanoparticles, to cool them and to manipulate them. And that will provide basically the source for this interferometer scheme to test, of course, things like CSL models to do interferometric tests. In the second part of this lecture, so depending on time, I will also, talk about these non-interferometric tests, and I think it's quite nicely, one can tell a story how it comes to also these non-interferometric tests. So I will try to do this. Okay, so levitated optomechanics. So Nikolai told you, of course, already all the important stuff about this. It is about trapping particles in vacuum. So here you see one of those experiments, which you also have seen already before, from Romain Cuidin and Lucas Novotny in the collaboration. So they did basically trapping. What you see here is basically part of a microscope objective, which focuses the light to a tiny spot, and then in this tiny spot, by using the optical gradient force, you trap a glass particle of about 100 nanometer or so, maybe 150 in diameter. So that is the experiment which Nikolai explained to you in quite detail. So here the difference is that you have a cavity, an optical cavity, and you trap the particle inside. And then, of course, you can use the advantages of the cavity to prepare, states of light, which you then can let interact with the particle. So that is, of course, the hope that that can be done at some point. Here is Peter Barker's experiment. So he is also doing levitation, but what he is doing is he's using a charged particle, an ion, and he has what he calls a hybrid trap. So he has basically a Paul trap, which is this thing here, which is trapping the particle and holding it. It's a very deep trap, it's very stable, so it's really easy to keep the particle, the ion in the trap, and then he is having an optical cavity which is overlapping with the trapping side, and now he can basically use the green potential here is the motion of the particle in the Paul trap, and that basically moves through these small wiggles here, which are is the standing field of the cavity, which also in combination of the two, it has an advantage for the cooling. Yes, we can basically now use many of those optical cavity potentials or mode potentials for the cooling effect. So all these shows you that there's quite a substantial effort on the experimental side to learn how to play with these little particles in vacuum, which of course has this potential for these fundamental tests of quantum mechanics. So here's our version. So Jamie, he's over there. So he will talk about this, or most of the stuff in next week in the talk. So I will tell it to you anyway. So here's the setup. That's the setup we use. And what you see here, the black thing, that's a parabolic mirror. And the parabolic mirror focuses light to a tiny spot, which is this here, and that's where we trap the particle. Yeah? So now what you see is that there are these different light fields which are indicated in this illustration. So the way it works is basically that you have an incoming laser. And the laser is now collimated to this tiny spot. Some of the light scatters with the particle, so that's Rayleigh scattering, because the wavelength of the light is much larger than the size of the particle. So the backscattered light goes back into the mirror and is recollimated. So that is this blue light field, while the majority of the light is not interacting with the particle at all. It is just diverging out. Yeah? basically leaving in this direction away from the mirror. So that is what we call the diverging field. And now what we can do is we can basically look at the interference pattern between these two optical fields, between the scattered field and the diverging field. And what this interference pattern or this interference should contain is basically a phase difference which carries information about the distance of this particle to the mirror. Yeah? That is exactly the difference, or twice that distance is the difference which the blue light has basically propagated more than the red light. So that is the phase shift which you see. And if you now imagine that the particle is basically jiggling back and forth in this direction, which we call the Z direction, then by this interferometric method, we basically see a phase shift of this interference pattern between these two light fields. Yeah? So if you would look basically towards this mirror, you would see an interference pattern like this. And now what you have to do is that is basically a snapshot. So if that would be like a movie, then that would like, breathe, would oscillate. So you basically would pick your detector at the right position and you could read the information of the particle position. So now the one trick which we basically use is that, as I said, much larger part of the light is not interacting with the particle. So that means that this diverging field has a very large intensity compared to the scattered field. And so to measure this interference pattern, or to have like a large modulation in the interference pattern, it would be nice to have a comparable intensity between these two fields. So a thing which you can do in the setup is you simply put your detector at some place, behind this mirror, where the diverging field, is diluted because it's diverging. It, gets the intensity measured in this area gets smaller and smaller if you make the distance longer, while the blue field, the scattered field, is recollimated so that approximately stays the same, not depending on the distance. So you choose basically the position where the intensity of the two fields is roughly the same, and then you get a large modulation which carries this information about the position. Okay, so this is a larger picture of this interference pattern. Now, the other thing which is also important, because it is an object which moves in 3 dimensions, yeah, so it not only moves in the Z direction with the spectral mirror, it also moves in X and Y. You can also pick up basically the motion along those directions. That is a little sketch which explains this. So here's the mirror again, and again you have the particle trapped here. And now if you think about the motion of the particle in this direction here, then basically the backscattered field will be slightly tilted with respect to the diverging field. Yeah? And so that is the same for the oscillation of the particle in this direction as it is for the oscillation of the particle in and out of the plane of this board. And then you have to position your particle, your detector at the position where you basically pick up this phase shift as well. And then you can also measure X and Y positions. Okay, so what you measure in the end, that's basically the signal of the photodiode which we use to detect this, is this here. So that's basically just the measurement of this field picked up at the specific location of the detector over time. And you see this oscillation. And now the next step is also explained by Nikolai already. Of course, if you have this time domain signal, you can basically get information about the motion in the frequency domain by doing something like a Fourier transformation. Before I show you this, I wanted to show you a movie, which is basically a 3D reconstruction, I hope it works, of the motion of the particle, which was done by Ashley. I think that's the wrong one. The PhD student group, so I will move it here. Okay, so now this is like the 3D motion of the particle in the trap. And so what you see, I cannot see the scales. Okay, so that's the particle trapped, yeah, and it moves in 3D. And here you see the projections along the different directions. So here's Z, here's Y, here's X. So that's real data. And you see that this is in microseconds, of course, forget about all this here. It's like 400 something microseconds. So it's basically a slowed down movie of the motion. But you see it's basically oscillating all the time. So the good thing about this movie, it goes about 5 minutes. So I can basically go out and have a coffee. No. But that is basically the system what we have. So now, if you look at this, yeah, I know I come back. Yeah. 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 I don't know. It depends on the experiment. Do you want to comment? Okay. Okay, so now that was the time domain. So now, again, here is a more complete version of the setup which we actually use. So the parabolic mirror is here in the vacuum chamber. Actually, what we do for the experiment is very similar to what Nikolai explained. So we basically have this chamber at atmosphere, then we use spray, a nebulizer spray, to get the particles into the chamber. We trap the particle, and then we pump down and keep the particle, and then at some point, if necessary, you turn on the feedback. So I will come back to the feedback, which is this thing here, in a minute. Now again, here's the motion, and what you get, of course, if you just measure with a single photodiode, is you get all the oscillations for X, Y, and Z motion together. Yeah? If you do a Fourier transformation, or if you plot the PSD of this motion, then you get a peak, yeah, which gives you the frequency of the oscillation. Depending on the power you use to trap the particle, that is in the region of 100, 150 kilohertz for the Z motion. Yeah. Yes, yeah, you will see it in a minute. Yeah? And that's also because of the geometry. I thought I have a plot for this. Let me go maybe forward to this one. Yes, yeah. So that is basically the full PSD, which you see here. So if you take the time domain, which I showed before, and you do this, you plot the PSD of that, then you get this peak here for the Z, and that is X and Y. So they're separated because, again, of the shape of the trap. And then these two here you can separate by playing with the polarization. So Jamie says it's correct what I say. That must be correct. Yeah, so you get them separated, and now the next step is actually what we want to do is cooling. So we want to basically reduce the temperature in each of these motional degrees of freedoms. So also Nikolai explained to you that you can basically use this area under those PSDs as a measure of the mean energy or temperature. So if I go back here now. So now the cooling here, yeah, that is done in a different way compared to the cavity. So what you do here is so-called parametric feedback. So the idea is simply that you modulate the trap stiffness, or if you want the shape of the trapping potential, depending on the motion or the position of the particle. Yeah? And so it works in the following way. So imagine you have basically this harmonic trap, yeah, the optical trap, and the particle sits in the trap. So now it has some kinetic energy, of course, so it means it moves, yeah, depending on the temperature of the particle. So now what you do with this photodiode detection, yeah, which I explained before, you basically know where the particle is. So when you see that the particle basically moves out of the center, you make the trap deeper so that it's much harder for the particle to climb up the hill. Yeah? So it would basically not move out of the center. You do this simply by increasing the intensity of your trapping laser. Yeah? You simply turn it up. If you instead see that the particle is somewhere in the extreme case and wants to move back, you don't want to give it a lot of acceleration by going down the hill, so you make the potential really shallow. Yeah? So you basically, in the setup, what you do is you turn the intensity down of the trapping field. Now the trick is that you have to do this switching between high and low intensity or high and low trapping powers faster than the oscillation frequency of the particle in the trap. Okay, that can be done. So I said that the particle oscillates with 100, 150 kilohertz or something like that. And if you have feedback, which is now this system here, which basically works at megahertz or 10 megahertz, then you're easily faster than the particle motion. So the way it works is you have, again here, the particle in the trap, that's the mirror. You pick up the position by exactly the same way as I explained before. You have a single photodiode, which is basically measuring the signal of the position. Then you put it in some electronics box, and that is where basically the parametric part comes. So what you do is you measure in the setup which we use a phase lock loop, so an lock-in amplifier, which is basically measuring phase of the motion of the particle, yeah, of the oscillation of the particle. Then that basically intrinsically measures the frequency of the particle. Then we twice the frequency and we add the phase to it. Yeah? And that is now the phase which is in principle doing the cooling part. Yeah? So that is like in a classical example when you have like a swing, let's say a child on a swing, and you want to stop it, what you do is you basically push the child when it's coming towards you. Yeah? So when basically the swing is coming towards you, you push against the motion. So what you do is you basically act with a different phase on this oscillation. That is exactly what this phase is doing here. So now that is done in an electronics box, and there are different ways to realize this. What we do is by FPGA electronics. So that is digital electronics, which you can program, which is very fancy, very complicated. But there's now someone who knows how to do it, or is learning more and more how to do it. That gives some flexibility because you can do, as I will show you later, you can do a lot of other stuff with this feedback here. Yeah? So cooling is just one thing, parametric cooling is just one thing which you can do with this feedback. So now, okay, so you detect the signal, you do this electronics trick here, and then you generate a signal, and that you give to an AOM, yeah? So an acousto-optic modulator, which is modulating the intensity of light, the light which is passing through. And then you give this light back to the particle. That's the feedback. Okay. Now the cool thing is that because these frequency peaks of X, Y, and Z, they're separated in frequency, you can do it for all three axes simultaneously. So what you need is you need three different feedback channels. So basically one of those electronic boxes for X, another one for Y, another one for Z, and then you sum up the signals after the three boxes and put it to the AOM, and then you can simultaneously cool all three axes of this particle. Yeah? Okay, so now there's something, there's a movie, I think it's Jamie in this movie. It's a very old one, it's maybe 2 years old. And this was, huh? No, that's not Jamie, no. Jamie is behind you, And it's a movie, which is basically you look on an oscilloscope, yeah, which is basically online doing this Fourier transformation, so you directly see the PSD of the oscillation, and that is just one, usually the Z. And I think it was maybe 2 years ago when we saw like the first cooling effect. You will see it is really experimental in the sense that it looks terrible. Yeah, so there's this big peak here, yeah? So now the feedback goes on and something really crazy happens. I think now they have much more control and it looks much nicer. But because that's historic, I wanted to show this to you. So you see after this, so the cooling goes on, and after this, you basically reduce the size of this peak here. In this movie, you see that you basically grow the other peak, yeah? So that is some interesting effect. So this is, I think, X and Y overlapping, so that is the motion of the other two peaks. And because this is done at high pressure, so let's say, I don't know, 100 millibar or something, you have a channel by collisions by which the two different, or the three different axes, they can talk. Yeah? So you can basically bring energy from here to here. Also, this is not regularly happening anymore, so we can control all individually, but that's basically, a little movie which shows you how it looks. Or looked like in the lab like 2 years ago, is that right? Something like that. Okay, so now again I have another movie, lots of movies. Which is again the 3D movie of the motion. And now you can, maybe before I start this, you can tell me what you expect to see. There's a difference if you look at the motion now. And now the feedback is basically on, but only in the Z direction. So what is it, what you expect to see? How is the motion different if you do cooling? Yes, exactly. That's very simple. So, there are variations. Again, that's a very short time snapshot of the motion. So if you would trace this for a longer time, then you would see fluctuations. So there would be also, small and larger amplitudes comparably. But overall, cooling basically reduces the amplitude of the oscillation. The frequency stays the same. And yeah, I think it's really nice. We can control it really good. I think this is cooling. It says 3 Kelvin. So you cool basically from 300 Kelvin room temperature to 3 Kelvin. And that was a little experiment which Ashley did, and then he just took. Yes, yeah. So there's noise, there's collisional noise. Maybe I should go back to there was an equation which I passed without mentioning, because I'm not the equation guy. But okay, so here's the equation of motion, yeah, which is like the harmonic oscillator thingy. So you have damping, which can have different contributions physically, but in the regime of most of the experiments which we do, that is by gas collisions, because there's still a significant amount of gas particles in the background which kick basically the particle and damp the motion. And you see here on the right-hand side, that is basically also the fluctuation term, which comes, that is also these gas collisions in this high pressure regime, because they come and they drive the oscillation, and they basically thermalize the motion to the temperature of this background gas. Then there is this feedback term here, which is basically the electronic thing which we introduce to at some point replace this here or compensate this here, and also use it for cooling. Yes, yeah. So as I said, so we start at atmosphere, yeah, and then we pump down, and the lowest pressure we could reach so far is something like 10⁻⁶, 5 × 10⁻⁶ millibar. Yeah? So that is, you would not call it ultra high vacuum, so that is high vacuum maybe. Yes. Okay, so now I showed you the trapping, the detection of the particle. So, you know, it is, compared to the cavities, it is really a very simple setup. And also this photodiode here, yeah, this detector, that is, you know, a standard photodiode which you can buy from Thor Labs or from other companies which sell this for not too much money. So it's not like sophisticated equipment which you need to do this experiment. Now, the thing which is a bit sophisticated is this guy here. So it's an EDFA. Who knows what EDFA stands for? Yeah? Yes, exactly. So that's a fiber amplifier. So that is basically the revolution of telecommunication and the internet. So that is what is basically in every thing which works with optical fiber. You have to have it to amplify basically the optical signal which is propagating along this, and that has been developed. It has actually been invented in Southampton, and now it is everywhere. And we use it because it is nice and stable. And also it has the great feature, you get it, you know, significant power at this, at the output, which is, you know, some watts, maybe up to 10 watts of CW, so continuous power. And all the properties of light are mainly determined by the seed laser. Yes, we have a seed laser, which is this guy here, which is of low power, so some tens of milliwatts. And all the properties of the seed laser, so all the, you know, the stability of the seed laser, so in terms of line width and intensity stability, that is basically propagated through the EDFA. So if you have a narrow line width laser here, something like a, I don't know, a 10 Hertz system or a Hertz system or whatever you need for your experiment, it basically goes through the EDFA and is simply amplified. So that preserves these nice features, which is, you know, a very good feature. So what we do is we have this very fancy seed laser, which is indeed a very good one. And then we have the AOM here, which is modulating the seed laser before it goes into the amplifier. And I think that helps a lot to get rid of noise in the system. Of course, you have noise from the EDFA, so intrinsically, you know, everything which is physical has some noise, but I think it is comparably low to other, you know, laser systems which you could build here. The other interesting story is maybe the mirror. Yeah, the mirror. I don't have an example. I also don't have a photograph. So it is a mirror which is machined with a very precise tool from a block of aluminum. So there is. That's also an interesting story. So I always thought. When James Bateman, he was a postdoc in the group, and he was basically the mastermind behind the setup. So he knew about EDFAs, and he knew about, you know, optic setups and how to build this stuff. And he told me, yeah, you know, there's this guy, and he in his shed he has this milling machine, yeah, which can mill very precise shapes. So they are talking about, I don't know if you have ever worked in a mechanical workshop. So if you consider to become an experimentalist, it's something which I highly recommend, because then you get the feeling what, you know, it's possible in this world. On the mechanical side, which is somehow the basis of then, you know, you doing the experiments on top of that. So typically what in a standard mechanical workshop, what these guys will tell you is that you can maybe machine something to some microns. Yeah? So that is the precision they can get for surfaces and for, you know, making a little feature here and there, but not better. So now these guys, they do it on the order of tens to hundreds of nanometers. Yeah? And the trick is that they have an optical interferometer, which is basically detecting the position of the milling tool with respect to the piece which they want to work on. And they claim that, for instance, the surface roughness of this mirror, so by how much you have wriggles here, that's only determined by the material itself, so by the grain size of the aluminum material which you use. So that's really cool. So I thought it's this genius guy who has this mirror in his shed, but it turns out it's a big company, Siemens Mirrors, and they have actually built components for LISA Pathfinder missions. So they're really like very sophisticated. But still, you may know that you know, if you want to have high NA optics, so optics like microscope objectives with a high numerical aperture, so where you can focus light really to a tiny spot, and you get a large angle for the focusing, so where you also would collect most of the light which is emitted from this tiny spot. So if you buy a microscope objective for this, you can easily pay a lot of money, and then it is a pain to get this stuff into a vacuum chamber, because usually these microscope objectives are tubes with a set of lenses, and in between is air or some other stuff. Maybe they have put in some fancy things to, increase refractive indices and so on. And you cannot easily put this in a vacuum chamber. Yeah? So, and that is very complicated and usually also very expensive to get those objectives into vacuum. So now this mirror, that is something like 500 pounds, so comparably cheap, and there's no problem to put it in vacuum. Yes, so you simply put it there, you clean it, you maybe bake it out if you want to UHV, and it's very, very smooth and compatible. Okay, so that is, some technical details for people who are interested. Again, yes, so back to mathematics. So this is the power spectral density, so the PSD, that's the equation for this. What we now can do is we can measure this PSD here, that's the blue dots, and then we can fit this exact function, which is the red line to it, and we can extract properties about the particles from this fit, so we can determine the mass, which is the size of the particle. That also, this equation contains like this damping coefficients. There's this extra delta gamma, which comes from the feedback. So if you introduce the feedback, that basically gives you a term here. You get basically the frequencies. This delta omega, that's an interesting one. So you, from other optomechanical experiments, you would expect that there is this delta gamma here, which is called an optical spring in optomechanics. So now we have tried to look for this. We don't see it. And I think I understand why that is. I have half convinced Mauro that that's true. And I think the reason is that we don't have optical scattering force in our setup. Yeah? So the trap is built so that basically keeping the particle at the position is completely determined by gradient force, right? So that is, you have the shape of your focus, so you have the gradient of the field, and that couples to the polarizability of the particle by the dipole force, and that keeps the particle in place in all three directions. So now there's this other force with Nikolai introduced, which gives this nice, if you have the meteorites, it gives you these two tails, which we have, yeah, which is basically the scattering force, which, you have from momentum transfer of photons to the particles. There's really, pressure, light pressure. So this trap, which we have here, is designed that the scattering force is really, really very small. Yeah? That also gives a limitation to our trap. It only works for pretty small particles. We can trap particles of the size of 25 nanometers in diameter to maybe 200, 250. If the particle would be larger, then the scattering force would become, dominating, and it would simply blow the particle out of the trap because there's only light pressure from one direction. Yeah. Yes, yeah, that's a good question. So I always say in my talks, but usually there's no student there. I usually say that, I thought it's a good idea to use 1550 because there are like issues with this particle which have to do with absorption. Yeah? So people, for instance, see that if the particle is not glass, if it's a different material, for instance, diamond, or many other things which people try to trap, they see that there is a lot of absorption. So they see that the particle basically gets cooked inside the trap. So if you have still oxygen in the chamber, you burn it. If it's in vacuum, then you simply melt it and it disappears. So you lose it from the trap. Yeah? And I think the problem is absorption. Okay. So the idea was to use a laser wavelength where absorption is typically low. Yeah? And I think the choices you have, if you look at the spectrum, in the visible range, you have all these optical transitions. In the near infrared, you have all the phonons, they start to come, but in between, there's a little gap, and that is almost exactly where you have the 1550. Yeah? So that was the reason for choosing it. So now, it's a pain in the ass because you don't see this light, right? But it's invisible. So if you do the experiment, you basically have to align something which you don't see, and that is my joke that I always say that when the students at some point realize that there are also lasers which are visible, then they will kill me. think that it should be either square root or square there. Yeah, only the one is a type. I hope it's not there. Yes. Okay. Yes. Okay, so there was the cooling. Now you can, of course, play with the cooling, and I should give you the number which we have reached. So now here you see the full beauty of it. So the red spectrum is basically the 300 Kelvin spectrum at 10 to minus 2 millibar. So there's always this play between the temperature you can cool, the center of mass motion, and the pressure you have in your chamber, because you have thermalization to the background gas, you have these collisions, and your heating rate from these collisions has to somehow compete with the cooling rate or the other way around. So you have to compare this. So now while you pump down, you basically keep your feedback on, and then you can cool these guys. So the blue little things which you see here is basically what remains. That here is from the Z, that's the X and the Y, and simultaneously you can cool to something between 1 millikelvin and 10 millikelvin. So that's the temperature which we have reached at the moment with this experiment. So we were quite thrilled by this, because at the time, which is now also maybe, I don't know, a year ago or so, it was the coolest reported, and for a short amount of time we thought, that is quite cool. And then Lukas Novotny, almost at the same time, he achieved something below millikelvin, and now everyone only talks about phonon numbers. So this temperature, if you have something like millikelvin, that corresponds for this system to something like 150 phonons. So again, it's a thermal distribution. It's a thermal state, but the mean phonon number is 150, and in Lukas Novotny's experiment, it is something like 20 or 24. Yeah, so he has reached his recoil limit, and Nikolai showed you this nice study of Novotny's group, where they basically show that there is this photon recoil heating effect. So now what you can do is you can play the game, and you can ask the question, so if we assume that there is basically no change to the contributions to gamma and delta gamma if you go down the pressure, so here's pressure and temperature. So if you basically extrapolate from the measurements which you have here, so you can see if you go lower in pressure, then you also go lower in temperature, which makes sense because you reduce basically the heating rate of your background gas, while you keep the cooling rate of the feedback constant. Then you would extrapolate that at this line, so where the straight lines basically meet the dashed lines, that would be the ground state of the system. So the ground state of the harmonic oscillator of this mechanical motion for X, Y, and Z, and that would be at the pressure, something between 10 to minus 8 and 10 to minus 9 millibar. So what people, of course, now have seen, so Novotny has seen, is that it levels off at some point because of recoil effect. So it's maybe still a bit hard, and one has to think what to do to go to the ground state. One of the options is, of course, to use a different cooling technique with this feedback pre-cooled particles to switch to a cavity and then use this to go to the ground state. Okay. Yeah, actually, because we discussed a lot Q factor, so the Q factor you have at these conditions here. So if you're in the 10 to minus 5 millibar range, you have already a Q factor of 10 to the 7, which is comparable to the best mechanical oscillators which you have. Again, it's not the full truth of the story. There are, as we have seen, also mechanical systems now which have nice large Q factors. But again, if you pump further down, this will go up. Again, if there are no other effects come up and kick in. Yes, so let me see. I maybe skip this. Okay, so now the bottom line message is that I guess if you remember the numbers which I gave you for the interferometer, for this Talbot interferometer, where we drop, then we have the grating, and then we have the slide to capture the particles. The requirement was that we need a particle of something like 10 to 20 nanometer in diameter, and we have to cool it to something like 10 millikelvin, and then this will be sufficient for a source. So that means that with the system which we have realized, with this feedback cool system, we basically have a source for our interferometer. So that would work for the matter wave interferometer, and what we do at the moment in Southampton is basically building this interferometer. So there's a vacuum chamber already, there's the source on the top, and then I'm trying desperately to get some money to get, put the laser in for the grating and build the detection system. But it will go on, and hopefully in the not so far future, we will have this interferometer. Yeah? So from the particle source side, we basically have a solution. But now you can see that it is such a nice system. Yeah? I have shown you that you have this little particle, which is, let's say, 100 nanometer in diameter, and in this optical trap, you can nicely observe oscillations, and you can use relatively straightforward mathematics like this equation of motion for the harmonic oscillator, damped or underdamped, depends on the regime, which you can use to actually, you understand what's going on. Yeah, it's so good. So we couldn't resist to try other stuff, having the system. And the first thing was squeezing. So I think that was basically the first squeezing of a levitated optomechanics. Nikolai told you about squeezing in cantilever optomechanics. And in a way, it is interesting because I think we do exactly the opposite to pulse optomechanics. I will come back to this at the moment, in a minute. So I first show you the setup. Again, it's this parabolic mirror. We trap the particle here. There's the laser, there's an AOM. Now we use a high power laser because it turns out if you have this EDFA, there are some time limits for the switching of signals. So if you have a fast signal before the EDFA will impose some delays on the signal. Yeah? So the EDFA will basically slow down the signal. So for some fast operations, you cannot use an EDFA. But what we basically do is we have a simple signal generator which generates pulses, which are sent to the AOM. And what it does is basically, again, it changes the power of the laser, yeah? And it switches between two different trapping frequencies, yeah? Two different trapping parabolas, which are at two different frequencies. And again, the trick that is very similar to pulse optomechanics, the switch has to be faster than the oscillation period of the particle. And what you see here is basically the time trace of two examples of such a switch. So what you do is you have a signal which is usually a high trapping frequency, which is it's a deep trap, and then we trap suddenly to like a low trap. We keep it there for some time, and then we switch back to a high trap. So that is just the difference between red and black here is that the duration or the time between switching down and switching up is different. Okay, so very simple setup. So now I think I have a movie again. I hope at least. Maybe it's in the presentation. Okay, so now maybe I should show you a different thing first. Okay, so what you see here is basically again a time trace of a signal, but this time it is basically the average signal over 1,000 of those experiments, which we do subsequently. So we basically have the trapped particle, we do release and switch back, and then we wait some time. Then again with the same particle, we do release, switch back, and then we do this 1,000, 2,000 times. And then we average basically the time traces of all this 1,000 samples. And that is the red curve, which you see here. So this is basically the time before we do the switch. Yeah? And you can see that it is an almost constant line. So there's an effect from filtering, because what we do is we only look at the Z motion. So we filter out X and Y. So we have a filter which is only looking at the motion in the Z direction. Could be, any of the others, but we just choose that because it was the strongest. And you have a constant signal here, which means that it is basically like the phase, yeah, of the oscillation is random before we apply the kick. So in the sample of 1,000 experiments, particle at a given time is at different positions in the parabolic trap. So now here's when the switch happens, and then you see that the amplitude of the oscillation basically goes up dramatically. You also, it's maybe hard to see here, but you get some sort of, I don't know if you can call it phase coherent, but you basically initialize the particle to, after the pulse be in a certain position, and then all of them basically are synchronized. Yeah? All of these 1,000 samples, which you do at different times, but with the same particle, are synchronized, so that at the same time after the pulse, they're in the same position in the trap. And then you see this decay, so you could also call this a ring down time. And the decay basically comes from, again, the background gas collisions. So now what you basically do is, through the pulse, we have the nice large amplitude oscillation, but because the collisions come, they randomize the phase, and they also affect the amplitude of the oscillation. And if you basically fit some function to this, then you get exactly the same collisional damping factor gamma, which you would get from fitting to the PSD. Yeah? So you can basically also measure the pressure with the decay of this, or the ring down signal of this oscillation. Okay, so now I show you a movie of the same sample of measurements. So what you see here, so that will move in a minute. Yeah? So that's why it's called a movie. So here again is the time domain, so there's no labels on this, but again that is the RMS signal of the position in that direction. This is time. There will be a little marker here which basically tells you where we are in the evolution. And then on the right-hand side there's the phase space plot of this, so that's velocity and position. And here you see the initial state before we do the operation of the squeezing. Yeah? So now, as I said, it's a thermal state, so it's around 0, and it has like a almost spherical distribution, as you would expect this for a thermal state. There will be basically, this state will remain at the background, so that you see the difference to the state which happens dynamically times later. I maybe just show it. Now the pulse. And then it goes down, right? Okay, so if I go back to maybe somewhere here. So here you see that is basically after we have done the down pulse, what happens is that now, because the potential is much wider, you give more space for the particle to explore. Yeah? So that is what I meant when I said that it is the opposite of what Nikolai and Michael Wenner did in the pulsed optomechanics. So there you have a pulse which is basically compressing in X direction. So what we do is we opening basically the gates, and the thing can expand in the X direction. So therefore, it gets much longer in the X direction. But because somehow the area of this distribution has to be conserved because of energy conservation, it reduces in the opposite direction. Yeah, there's yeah, so that also, it's a good question. I think it has also to do with alignment details. We have never really figured it out in all the details. You see it's slightly different when you do more experiments, so it's not always consistently going in one direction. And I think it means that maybe the wider trap is more sensitive to the minimum position, and if that basically shifts a little bit, or if you apply the pulse, it shifts a little bit the position of the pulse, then it dislocates. So I don't think that it is an important feature of the overall dynamics. Okay, and then again, as in the example yesterday, of course, the evolution of the harmonic oscillator gives you basically the rotation and phase space, and if you then move on, then this state basically rotates, and then what you can do is you can basically, when you do the reverse operation, yeah, you can optimize the amount of squeezing. So if you do it with T over 4, I think it is. So if your squeezing pulse is a quarter of the time for a full oscillation period, then you get the maximum squeezing. If you do half, then you basically hit the distribution when it is basically half rotated, so you can compensate the squeezing effect completely. So now, I think if you would do the operation the other way around, so if you would start with a white and would go to a deep trap, then it would be more like a pulse mechanics operation. So that would be basically give some confinement, and you would really compress the ensemble in a confined state. Yes, of course, yes, I should say it's completely classical. Yeah, it's a thermal state. So it's nowhere near minimum uncertainty states. It's nothing to do with Heisenberg's uncertainty. So it's it's a huge thing. But I guess so if you could pre-cool it, if you could cool it to a low state, if you could go closer to a minimum uncertainty state, then it would become at some point some sort of real squeezing in the quantum mechanical sense. But at the moment, it's all classical. It's just to show that there are these ways of manipulation where you can generate this. Right? And then there's the hope, of course, if someone achieves, or maybe we achieve to go to the quantum regime, that we can use the same. Yeah. Okay, so yes, that's right. There was no cooling, and it was also comparably high pressure. So again, it was just to show the operation. But Jamie is actually doing now experiments where we try to do exactly this. So you cool by feedback, and then you do the squeezing pulse, and you do this repeatedly. So you cool and squeeze, you cool and squeeze. And of course, you can also do, that is just a single pulse. You can have a sequence of pulses. Then you should increase basically the effect of the squeezing. So that is, optimization which we now try to do. Yes, sure. Yes, yeah, you see that there's this cigar, and then this rotates, and then it thermalizes back to the spherical distribution because of collisions. Yeah. Yes. Okay. So here's a pretty picture which shows the snapshots of this dynamics, but it's essentially the same message. So you start with it's not it's not really spherical. It's a little bit of an ellipse, but you can increase the ellipticity, and then it rotates and becomes spherical. Okay. So let me see. Yes, so you can do more states. You can also do this. Again, it's all classical, but what you can do is you can basically do a ring state. So also you have seen something similar yesterday. So if that would be, quantum mechanically, if that would be minimum uncertainty, if this area here would have something to do with Heisenberg uncertainty relation, then it would somehow look like a number state or a Fock state. But again, it is not here, of course. It's just a classical thermal state, which is where we messed with. So what we do is basically we do cooling from this side with the feedback. Yeah. So the effect I have not mentioned so far, but of course, if you do the cooling operation, then you start with a very wide thermal state. Yeah. And if you do cooling, then you basically decrease the size of the state, the thermal state. So that is what we do here, and that is indicated by basically the cooling force, which pushes from the outside and makes the circle smaller. And what you then can do is you can have a heating force, which is basically almost random signal, or heating signal, which you put in with a function generator, and you basically empty the inner space of this distribution. So what it means that you find basically your, your states only sitting distributed on this ring here. Okay, so here are the experiments. So that's now basically playing with the parameters of this of the heating and the cooling. You can see you can make nice rings, yeah? And of course the question was, because it's so hard to go to the ground state in basically pushing it to the center, can you do, and to reach basically something non-classical, yeah? So can you do the opposite? Can you basically press it into a really narrow ring where you then can show by using, I don't know, Wigner functions or whatever you want to use as a tool to show non-classicality, that you have a ring which has a distribution which is narrower than it would be allowed from, classical laws. Of course, and not surprisingly, what you find is that you limit it, at least at the moment, by the same noises and the same limitations which prevent you from going basically in the original configuration to like a small state in the center. But that basically is the area of these guys here, which is basically proportional to the temperature or the mean energy of the motion in that direction, depending on the driving strength, which is basically the heating by which you heat the population from the center into the ring. And you can see that you're not really, you cannot see it from the units, but what you reach here is basically temperatures which are comparable to what we also had in the usual feedback cooling of the thermal state. Okay, so now again, so if you think in this kind of phase-based picture, what you're tempted to do is you think about like a toolbox, yeah. Again, that was mentioned by Nicola yesterday for cantilever optomechanics, where they have this. If you're in the sideband resolved regime, then you have a lot of nice tools which give you a really quantum toolbox to engineer states in the phase space. So the idea is if one can do something also here with this system, so if you have what is the set of operations you need to generate Gaussian states in the phase space, and what you need is basically cooling, squeezing, and displacement. If you can do these three things, then you can make any state. So what is missing is basically displacement, and that's here. So the way this has been done, that's also an experiment done by David Hempston. Again, here's the parabolic mirror, here's the trapping site, here's the particle sitting, and then relatively far away, a few centimeters, is a little needle. And what we do is we apply potential, an electric field, voltage to the needle, and that generates an electric field, and that electric field is now, pushing the particle, or is affecting the particle. The other reason why we actually also did this is that this is a way you can measure the electrical charges which are sitting on the particle. So what I have not mentioned, which is a secret, so don't tell anyone, is that if this particle are charged, then this nice interferometer scheme, this Talbot scheme, does not work at all. Yeah, so they have to be neutral. So now we need a method to first see if the particles are charged or not. And if we find that charge, we need to basically remove them from the experiment. So we have to pick only the neutral ones. And if you know a little bit about chemistry, colloidal chemistry, nanoparticles, if you talk to a chemist and you talk to him, I have this dielectric particle which comes from a solution, and then he said, of course, they're always surface charged. You cannot avoid this. These things are always charged. Come on, what are you talking about? So now, what we find, luckily, in this experiment is that about 1/3 of those particles is neutral, yeah? But the others carry charges, and now you see the different distributions. Those are now for different voltages, and you have, let's say, one electron charge sitting on the particle that displaces this by, I don't know, 50 nanometer in this case. If you increase the voltage, it goes further away. But what you basically get is like a scaling law, and that if you know the potential, then you basically can know the charge of the particle. So if it would be like twice of the charge, it would go to a different position. Yeah. Okay. Yes, so that's this experiment. Yeah. Yes. Yeah. So you can, you could in principle start to play with the chemistry, right? So it's like a, to me, it's like a vast material science question. Yeah, how to do this? There are so many possibilities, and there are so many. It's such a complicated system. So at the moment, I think we try to be lucky. We just take what is there, and then just to pick the right thing. So try to pick the particle which is not charged. Yeah. Okay, so then there's an, in principle that is a very similar experiment. What you can do is you can now study heating in this trap. So the idea is that that could be also interesting for force sensing. Of course, my interest in this was to look in something like this collapse models effects, which are heating effect. So what you do is you basically take your particle, you cool it as low as you can, and then you turn off the cooling, and then you simply observe how long it takes, for the particle to heat up, to go back to a higher temperature. And now, depending on the heating mechanism, you basically you get different time scales, right? So if you could in principle do prevent a lot of known heating mechanisms, for instance, as background gas collisions or heating by laser, things like that, then maybe at some point you could see and identify a non-conventional heating which comes from collapse models. So that would be, then of course, would need to be done a very careful analysis of this, as Andrea Vilante did for the magnetic cantilevers. But that would be a way to do it, and you have seen it already yesterday for the recoil heating. That was also the way Lukas Novotny basically analyzed this recoil heating effect, because there he also, from the theoretical model, could basically predict basically the slope of this curve here, and could measure it. So you could also use it for force sensing. So here, for instance, you again have a charged particle, and you have this potential, and depending on the geometry, you can basically measure the Coulomb force acting on the particle. And here you see the difference between, that is now really like I didn't even write down the numbers for this, but that is a very, very strong force. So that is, much stronger than, compared to the forces which Andrea was talking about. So we have very large voltages here. So we have, and then electric charges. So the Coulomb force is very strong, but at least you see a difference between applying a voltage and applying no voltage to this little needle. Okay, so then you can also do different experiments in terms of sensing. So I told you that I did a lot of different things so far, also experimental-wise, and I actually did my PhD in surface science. So for some reason, I'm still interested in surface interactions, and especially the weak ones, so van der Waals and Casimir-Polder interactions. So what you can do also with this setup, and that's an experiment which George Winston in the group did, is you can have, again, the same famous parabolic mirror trap with a particle. And now you have a silicon wafer here, which is transparent to 1550 laser light. And you trap the particle, and then you basically move the silicon wafer closer and closer to the position of the particle. This is what's shown here. What is plotted here is basically some sort of, I would call it an unharmonicity effect. Yeah? When you basically move the surface closer to the position of the particle, then the interaction of the particle with the surface is affecting basically the shape of your trapping potential. So originally it's like a parabolic potential, but you can, I think, easily imagine if you have now the surface here, then it is basically distorting it, so it becomes more like an anharmonic, like a Morse potential or something like that, which means that if you look at the PSD, the power spectral density of the motion, the peaks get larger, so the area gets larger. It looks like a heating effect, but it comes because of the anharmonic shape of the trapping potential. If you analyze the area of the PSDs, which is basically plotted here, and you convert this into something like a particle energy, which is a bit more complicated, then you can get plots like this. And the fit he has done here is basically for a van der Waals interaction with a Hammaker constant, which fits for the materials, so that Hammaker theory is used for this sort of weak dispersion forces. It's very approximate, but it's the best which they have. And the hope is that at some point maybe one finds an effect, or maybe that's an interesting parameter range to look at this surface forces. But you can also do it with the with the same particle. It's basically very similar to an AFM, but now the particle is levitated. Yeah? So one of the ideas is actually to scan this surface in like an XY direction, and then you would, measuring these forces, you could basically make a 2D image of the topography, like in an AFM of this system. Now again, this guy here potentially has a much higher Q factor within the limits of, one still has to understand all the effects which influence the quality factor. But in principle, it can be much higher than for a standard AFM tip. So maybe there's, something which is interesting to probe with this because it has a higher sensitivity. What is also interesting, which I didn't know, is that, of course, if you have these two systems here and you have light which is in between them, you can have like multiple reflections, and you can have things like optical binding between the particles, which is, I think, an effect which has not been seen in vacuum. In solution, they do it quite often. They're quite interested in this. And it seems that if you have this optical binding, that also looks like a dispersion force. It would have much probably very similar scaling than this here. So that is, of course, something which we have to understand if that affects also our measurement. So if basically the energy or the force which we measure here, if that is just a purely optical one, or if it's like a van der Waals. But it's interesting stuff. Okay, and then that is basically the latest excitement here. So if you have the particle, yeah, and what we have observed is that when you spray the particles in a trap, and sometimes you have something which is really ugly, so it doesn't stay in a trap. So we have usually ignored this and have not, considered this. We just removed it and have waited for a really nice one, which was behaving well, which was giving nice spectra. And what we actually also never have done is when we had an ugly one, we never looked at the high frequencies. Yeah? So now if you imagine that this is particles in solution, yeah? And they're made, so basically they're all different. They have, of course, not always in perfectly spherical shape. So you can easily imagine that there are particles which are slightly elliptic. So if you have such particles, then you can potentially also see rotation. And that is what we see here. So here's the power spectral density. That's the low frequency range. That's the usual range where you see translation. So again, here's the Z and the X and the Y. And then if you look in the higher frequency range, which is megahertz, then you basically see this guy is popping up. So at 1.7 megahertz, that's the frequency of the rotation. Yeah? And you see higher harmonics of this. What is the nice thing is now you see basically the sidebands of the translation are modulated through this rotation. So now you see here that's the Z motion, the X and the Y, minus, 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 and on the other side, plus, plus, plus. You see the right scaling of pressure. What you, of course, expect is if you have this rotating particle, that if you reduce the pressure, then basically the rotation speeds up because the medium is not preventing the rotation anymore. So there's no friction in the medium. And that is what we see. So if you reduce the pressure, then the frequency goes up. So that's, of course, not the first time that people have seen rotation. So Markus Arndt, I'm pretty sure he will mention it in his talk later this week. So they have done beautiful studies where you see like picture book rotations of those nanoparticles. They have done it with silicon rods, which were, nanofabricated. They have a regular shape, and it is, really beautiful. There are other papers where they report on rotation. The interesting thing here is now that you basically get the rotation for free, right? If you just look at the ugly particles in your trap, you see the rotation. So that's just a hypothesis, so which has to be proven. My feeling is that, people have a lot of problems with these traps. Yeah? So they trap at high pressure at atmosphere, and then they want to pump down. In many cases, they lose the particle. So what would make sense to me is that to not lose the particle, you have to basically feedback control all the degrees of freedom. Yeah? So X, Y, Z translation, but also the rotation. So now, what we want to try to do is to do the same feedback cooling, which we do for X, Y, and Z, also to do it for the rotation, for this guy here, and then to try to pump down. Yeah? Because this ugly particle is usually a particle which you cannot pump down. So you cannot reduce the pressure, and you cannot keep it in the trap. It will, at some point, it will escape. And to me, it makes sense that the reason for escaping is that it goes up in frequency. At some point, it maybe jumps out of the trap. But if you look at these frequencies here, so they go into the tens of megahertz. Yeah? So that is basically, you have centrifugal forces which are basically pulling the particle into pieces. Yeah? So, and now I know, yeah. The other rotation, the first rotation actually was done by Kishan Dolakia in St. Andrews in the UK. And he is with this rotation, he's in the Guinness Book of World Records, because what he did, it was something like 40 megahertz or something rotation. That's the fastest man-made rotation, ever done. Yeah? So that tells you that it's, crazy speeds compared to material properties. Yeah? You can easily destruct the particles. So, okay, so I don't claim that it, fully resolves, the issue of when you cannot trap and keep particles, in your trap when you pump down, but it's certainly an effect which plays a role. Yes. So you do it in exactly the same way. So you pick the frequency, you lock onto the frequency with your phase lock loop, and then it is also described, of course, by a sine function. So you pick up the frequency, you twice the frequency, and then you add the phase. So you measure what you can experimentally. You can just do it online. So you basically monitor the rotation frequency, and then you change the phase, and then you can see, hopefully, that it slows down at some point. There's one more interesting thing here. There's actually another frequency, which is indicated here as F2, which is not moving with pressure. Yeah, so it does not have the same pressure dependency, or not moving is not correct. So it's not basically reducing. It's not increasing in frequency if the pressure is reduced. It's doing the opposite. So if you basically reduce the pressure for this one, it also reduces the frequency. So it cannot be a rotation. We are still a bit puzzled what it could be. So if any of you has a nice idea what it could be, I'm open for discussion. Okay, so that is the rotation. And again, so another interesting thing about this is when you talk about, quantum mechanical experiments and things like that is, you have seen from Nikolai's talk that if you can cool to the ground state, yeah, if you achieve this, then there are many ideas what you can do to prepare non-classical states and to use it for something useful in the sense of quantum mechanics. What we tried to do so far, and what you can actually see all this matter wave interferometry experiments where you use gratings to prepare superposition states, that is basically avoiding to have these technical difficulties to go to the ground state. Just try to do something non-classical with whatever you have. But of course, it is much better to do it properly and go to the ground state and then you start. So now the ground state of this here, it is in the range of millikelvin. So that's the temperatures which we reach for the translation easily by feedback. Right? And that is simply the same argument. Again, you have a high frequency, so it's a harmonic oscillator at a higher frequency. So therefore, also the ground state energy or ground state temperature is higher. So now, it maybe remains hard to go to the ground state for the translation of this particle, but maybe it's not so hard to go to the ground state of the rotation. And then you can start to think about rotation, and there's maybe a lot of things you can also do in terms of non-classical experiments. You can also prepare superposition states of rotation. Yeah. That is, I think it's an interesting opportunity. Okay, so I don't know how much time is left? 15 minutes, okay, that's great. Okay, so there is now the second part. And so it was like a longer lecture, but I think I hope you still see like the line of arguments and the way it was constructed. So I was talking about matter wave interferometry experiments. And then basically the first part of today's lecture was a lot of technical stuff on how to do it with these nanoparticles. But now going back to the original question, how to test those collapse models. Yeah? So of course the first candidate, and that is this matter wave interferometry. So historically people were thinking of this, and talking to Angelo, he always convinces me or tries to convince me that is the proper test. Okay, but there may be others. So the story I want to tell you is basically, along these lines, are there other methods which you can do to test the quantum superposition principle in the sense of testing those collapse models? Yeah? And of course, you know already the answer because Angelo told you and Andrea told you, and Andrea has this experiments, and he maybe gets a Nobel Prize for this. But here's the story. How to. I think it's quite interesting. The way to try to think about this for this different effects. So what is the idea about this non-interferometric tests? So the idea is, of course, that if there is this collapse effect, if there is this additional stuff which you add to the Schrödinger equation, which describes anything which is out there, then this means, if you take it seriously, that there is like a classical random field, yeah, which is universal, that basically fills the universe and affects any system which is there. Yeah? So now the question is, how does it couple to those systems, and which system would be the best to actually see the effect? Yeah? So what is sensitive enough so that you can see the heating effect, which is large enough so that you can, that it couples, sufficiently so that you can see it. So that was, along those lines was our thinking. It's not a long time ago, yeah. It's actually 2-3 years maybe with Angelo. And the first idea, of course, yeah, it feels like forever, yeah. It was like an explosion. Yeah? So that was before we had this nice Angelo's baby map, the parameter map of lambda and RC. Yes, of course. So that was the collaboration, yes, with the review paper. Yes. Okay, so the first idea was, motivated by quantum optics. So in quantum optics, there's a similar story, which is the story of the lump shift. Yeah. So also there, you basically have vacuum fluctuations, which are predicted by quantum field theory. So that is also some sort of noise, which is now affecting every quantum system. You know that was very famous. The first thing which was detected as an effect of quantum field theory. Yeah? So since discovery of the lump shift, it was clear, you have to do quantum field theory to describe the system. So now here, it's the same idea. You have the two-level system, which is this guy here. So excited state and ground state. And you have this, the usual, light-matter interactions or whatever you want to have to describe this. But now you have basically an additional noise which is affecting your system. So if you think about the system being in an excited state and there's this noise, yeah, then whenever you think about broadening mechanisms or something like that in two-level systems like Doppler broadening or collisional broadening or so, then it is always noise which is somehow reducing the lifetime of the excited state. So now our noise would do exactly the same. Yeah? So what you predict is something that, like your original, function of the emission. Yeah. So PSD, or however you want to call it, the spectral function, that would be shifted and broadened. Yeah? That's the two fundamental, effects which you can expect. And then what we did is the following. So it was Mohammed Bahami. He was the postdoc, basically doing the calculations. So he looked at all sorts of different two-level systems and also double-level systems. So like, we were looking into things where people do ultra-precise experiments, yeah? Like in hydrogen spectroscopy, hydrogen atom spectroscopy, like Ted Henge, where they measure to an incredible precision the transition lines, and which was a system where they discovered things like lamp shifts or so. And we looked at double-level systems like, the ammonia molecule, where you have this umbrella transition. So you have basically in H3, yeah, so you have hydrogen atoms, 3 hydrogen atoms, and 1 nitrogen, and now the nitrogen is basically tunneling through the plane of the hydrogen atoms, and that can be described by, tunneling through a double wave from one side to the other. There's a certain frequency, and you can measure it, and the noise should basically disturb the system somehow, the collapse noise. So we did all this, and what you find is numbers which are incredibly small. So with today's technology, you have no chance to see this effect. It's so tiny, you have no chance to see the collapse effect. So that was a bit disappointing, but we didn't give up, and then we thought, okay, so maybe we have to think about something else, and that again was together with TP. So if you think about, again, like a nanoparticle, or it could be also a larger object, yeah, then because of the mechanism which Angelo explained to you last week, I hope you remember, that if you have your collapse function, which is not exactly overlapping with the position of one of the states of your, let's say, superposition state, then you get like a slight shift of the position of the particle. So it looks like a diffusion. It's like a Brownian motion. So you can think about this effect as a Brownian motion effect, and have a very fancy simulation of this effect. So if you imagine this is now one of those levitated particles in the cryostat in a vacuum chamber, so that you don't have any conventional Brownian motion by particles which kick this from the outside, or photons which kick this from the outside, then it should be completely at rest. But if you would carefully look, and you basically would, assume that there is a collapse effect, then you should see this. Now I do this effect. I can do it back and forth, and I think that's the power of PowerPoint. Okay, and we wrote this down together with TP and Chayantani. I'm sure I did it wrong again with the name. Yes, and that was a paper. Basically, it was picking up on an old idea by Philip Pearl, so one of the founding fathers of CSL, which is basically saying, okay, so if there's this CSL noise field, then there should be a Brownian-like motion of a particle, if you can observe this carefully enough. Okay. No, it's not, so you should talk to Angelo. What happens in the collapse is actually, it's not becoming classical, it just becomes incredibly narrow, so that it appears to be classical. But it still, evolves according to quantum mechanics, so it still spreads after this, and then the next kick comes. So it depends on the rates of those kicks, how narrow it remains. So it can easily, increase again. Correct? Okay, and then the next step was basically to think about optomechanics, and that was really, I think, getting a lot of attraction. So now the idea is you take one of those big optomechanical systems. So here you have the fixed mirror, here you have the movable mirror, And you have learned a lot about this already from Nikolai and Andrea. So now if you simply assume that on top of all the noises which you have in the system already, you now also have this collapse noise, the lambda, yeah, which also kicks your oscillator. Would it be possible to see, to see such a heating effect? And so Mauro did this calculations, Mauro Paranostro, and he is basically a chopped off power spectral density. So there would be like the head which was chopped off to show the difference, which is again a very small effect, but it's visible. And what is calculated here is basically the red one is with this noise of the collapse effect. The blue is without. So if you basically measure the PSD precisely enough, then you should see if the CSL is not there or if it is. And I said, there was some discussion about this. So we did a mistake in the details of this. The effect is actually depending on the geometry. So there are many more details where you have to take care of. It depends on the geometry of the mechanical oscillator, how sensitive it is, and also the scaling, which is shown here. It is it seems that it's not like this. So this I is basically the difference between with CSL and without CSL. And here it shows that it scales up with the mass, so it becomes stronger and stronger and stronger. If you have a large mass, that's not true. So in more careful analysis by Stefan Nimrichter and Klaus Hornberger and Clemens Hammerer showed that there is like a resonant effect. So you basically, if you want to look for a specific CSL model with specific parameters, lambda and RC, then there's a specific geometry, which is, the shape and the size of your system, which is the ideal probe for this. That makes a lot of sense, I think, with what we have learned since then. So the next slide is, of course, what you have seen already. Yeah. It is, of course, in the details, very different from this. So it's not an optomechanics experiment; it's a magnetic experiment. I cannot repeat all the details of this, but I think the basic effect is the same, right? So you basically measure very precisely the temperature. I mean, when you measure this here, what you do is, again, you integrate the area of the function, which gives you the temperature. So if you have a system where you can very precisely measure the temperature, yeah, and which is massive and fulfills all the criteria to measure this, then you should be able to see it. So now what you have to find is like the system in Andreas' case, which is really sensitive enough, which is isolated enough in the fridge and in vacuum, so that you can be able to see this. But I think the effect is such, it is the heating effect from Pearl's effect is predicted. It is. Yeah, that's interesting. So Nikolai mentioned this already to me in the break that there are much probably already optomechanic experiments which have been performed, which are very sensitive and which have a very high resolution for measuring the position of these oscillators. Yeah? So they're very good in doing this, and I'm pretty sure that there is data out there which contain information which are useful for the map. Yes. Yeah. I mean, it's an interesting point. Yeah? I mean, if you say that even if the size is changed, then it is. Yes, and that would be something very exciting. I mean, so I think the first step would be to see if there's really CSL noise, and then to me the next step would be to see if there's a color, if there's a spectrum, which would give you an indication what is the physical process which is behind. That is something which, you know, we didn't say very clearly so far, but you know, this model is there, but the physics is completely unclear, right? So what is the physics reason for these collapse effects? And if you see like a spectrum, if you see, you know, like a fingerprint of this interaction, that would be extremely cool. Okay, yes, I'm almost there. I think that's basically it. Yeah. So let's end here. Thanks.
Questions? No questions. Okay. Let's thank the speaker.
Was long enough. Thanks.